Now, as we have seen what vectors are, let's see how we can add them. Let's have a vector A, for instance, representing some displacement. An ant might have gone up and to the right, and then it has moved down and to the right. So here's the vector B representing the second portion of that displacement. So how do we add the two vectors to find the total displacement of that ant? First, let's remember that vectors are not fixed in space, but simply they tell us how much we have to move downwards and to the right so that we can actually move from their tail to the tip. So if you remember that, then you can recognize that I can certainly shift my vector anywhere in space and it still will be the same vector as before. So I'm going to move B here so that its tail coincides with the tip of A. And now the picture is very intuitive. I can actually draw directly the result. If the ant moved along the vector A and then along the vector B, the total displacement will be a vector C that starts from the tail of A and ends at the tip of B. Because in this configuration, we actually move the tail of B to coincide with the tip of A. This rule is known as the tip to tail rule. Now, there is another configuration or another way to visualize what is happening. Let's look at the vector A again. Instead of moving B to the tip of it, I could have actually moved it so that both tails coincide. Or in other words, the vectors have the same origin. What would be the sum of the two? Now the answer should be the same as before, and I know that if I were to move vector B back to the tip of A, I know the answer would be vector C here. And now I can recognize a pattern. C appears to be the diagonal of the parallelogram formed by the vectors A and B. It's the diagonal that starts from their tails. And because of, again, this visually appears as a parallelogram, we know this is the parallelogram rule. They both are identical. They will always give you the same answer. It's the difference comes that sometimes if you're dealing with displacements, the tip to tail rule will be the more natural state there for you to trace someone's displacement. On the other hand, if you're looking at an object and you have many forces acting on that, the parallelogram rule will emerge simply from drawing all the forces acting on that object. What about subtraction? Well, even though there are rules for subtraction, I actually like to use algebra here and pretend that the vector d, being the difference between a and b, is simply the sum of two vectors, a and minus b. So that brings me back to the rules of vector addition. Here's the vector a, here's the vector b. I will need to move vector a, so let me move it here so I can actually have space. And next, what I'm going to do is to flip the vector b so I can construct a vector that is called minus b. Then I'm going to shift it to the tip of a and use my tip to tail rule to see that the vector d here, that is going to be the sum of the two vectors, will be a minus b. There is a pattern here and some students like to memorize it. And that is what I meant by saying that there's a rule about subtraction. And you can see the pattern if you move here the vector a and work back with the original vector b, and then you shift the vector d that we found that was a minus b, and you see now that that vector d is going to simply point from the tip of the second vector b to the tip of the first vector a. And that is what students usually memorize as the rule of subtraction. Once again, I rarely memorize that rule. Usually for myself, I like to shift back to the rules for subtraction. All those rules are really nice if you're trying to visualize what is happening in a physics problem. But as soon as the question shifts to what is the exact value of a particular displacement or how much is the total force, it's very difficult. I mean, you welcome the rules from geometry and theorems. I have seen students, brave souls, who went and used the sine theorem and the cosine theorem from geometry and triangles, and you're welcome to do that, but they're not very practical. And the moment someone gives you 3 or 4 vectors, it becomes very cumbersome. And there's really no need for us to go this way if we need numeric answers. The easiest way to add vectors when you're after a numeric solution and specific answers for the length of a particular vector and its direction is to do the vector addition by components. So let's go back here to our vector A, and let's imagine someone has already figured out the components of that vector A. Presumably, we already knew the magnitude and the direction, so we have calculated the components AX and AY. And let's say we have done the same thing for the vector B. We knew its own angle here, probably phi, not necessarily the same as theta, and we have calculated its components bx and by. Now the question is, what is the sum, the vector c, that is really a plus b? Here the rules for adding vectors by components. They're very, very simple. The x component of c will be simply the sum of the x components of a and b, and the y components of c, the y component of c will be the sum of the y components of a and b. You have the x and the y components of the resultant vector. Now what you need to do is go back and find the magnitude using the Pythagorean theorem, and using the tangent function you can also find the angle that will give you the direction of that vector c. You see, it's very straightforward, very nice and clean, as long as someone has calculated the components for you. In a normal problem, you might have to do those steps yourself. So you'll have to do some preliminary steps to figure out the components of A and B before you can go and add them. The downside of this method here, this approach, is that even though we know the answer, we really have no idea how the vector c looks. So how does the vector c look? You could go back and use the tip to tail rule or the parallelogram rule to draw the vectors and see how they look. So here's the vector A, here's the vector B, and you can draw and see, aha, so the components Cx and Cy and the magnitude and the direction and the angle gamma that I calculated earlier really represent this vector C, that is A plus B. In terms of its components here, I will need a coordinate system, so let me bring that xy coordinate system. What this means is that this is going to be the angle gamma, for which I know the tangent of gamma is going to be equal to Cy over Cx. And of course, I will have the component Cx and Cy marked on that coordinate system according to my calculations. Now, what if you need to calculate the difference between the two vectors? Well, you do exactly the same, only now you're going to subtract the components. The x component of vector d will be the ax minus bx, and the y component of d will be ay minus by.